So Notebook 3 is encouraging us to move to a different direction. So Notebook 1 emulates analysis that can be performed on your local machine. It is so typically these are small scale analysis with say one or maybe a couple of subjects. You can run it on your own laptop. It won't take too much time. You can quickly look at the data um, and then be done with that. Notebook 2 um, goes in one goes one step further towards high performance computing, and it it encourages us to look at how to process large data, large data sets, potentially with high performance computing. When we have access to clusters, we can or to computational resources, how we can um, process multiple subjects at the same time, how we can train large models, something that would not be really achievable on a single machine. In our case, we were able to do it in Google Colab because the dataset is still pretty small. But if you switch to what Ajay is doing on Fabric, he is doing similar things with fMRI datasets where it really takes a very long time to process them. And I wouldn't attempt doing that on a local machine unless you're willing to keep it fully plugged in and wait for it to finish for some hours. On Fabric, with proper parallelization, it can be done much faster. So this is a step towards one direction, towards HPC from the local machine. Now in Notebook 3, we will be dealing with a step towards a different direction, towards embedded devices. So the laptop is in the center, HPC on one side, and embedded devices are on the other side. Embedded devices are like laptops, but they are way more limited in terms of the hardware you can use. Typically, they have simpler processors with which are much weaker compared to the even the laptop processors. They have really limited amounts of memory, so you cannot really run um, large analysis on these devices. You can only program them to perform very simple tasks. An example of an edge device could be, well, in the modern days, even a fridge or an oven or something like that, where we cannot really perform something, some heavy computations. We have to account for their inherent limitations. And so here in Colab 3, we will try to think about how we can run some simple analysis on a simulator for such a device. So let me briefly talk about the what we are simulating here. So we are working with a simulator of the BBC Microbit V2 microcontroller. Um, Let me go to their website. So this is what it looks like. It's a small chip with, I think, one processor core. Um, do they have a better picture of that? Yes. Okay, let me run this video and pause it immediately. It comes in this box. Okay, great. So this is what it looks like. Uh, it's a small chip. It has one, I think, one processor core. It has an LED display. It has two buttons. General input-output configuration, and then it has a touch sensor, a temperature sensor, and some other sensors like the accelerometer and some others. So this is what the front looks like. Okay, this demonstrates LEDs. And this is what the back looks like. So the back is just essentially a circuit that runs the whole thing. We are using this device as an example because you can even order it and buy it yourself from Amazon. I think it costs $20, and I'm not advertising anything. I'm just saying that it's a nice device, embedded device to play with, um, because it really incorporates. You can conduct a lot of interesting experiments with it and really have a feel for what an edge device is. Here on the Microbit website, they even have, let us see. Yeah, so they have examples of experiments you can do with the microbit, such as an animal tracker or okay, yes, here are the projects. So they have projects that you can perform with this microbit. So they range from simple projects such as just displaying, say, a heart on the microbit to very interesting and advanced projects. So for example, if you go to, I don't know, physical education, you can program this device to act as a step counter or as a kick strength detector. Uh, I think you can program it to perform computations to serve as an alarm clock. You can log data from it. Solar panel experiment, evaporation experiment. You can log data from the accelerometer. Um, I mean the movement data. And in one of our other workshop, which specifically targets microbit, it's a machine learning oriented workshop. We use them on site, and we actually record data from the microbit in real time, and we train a simple classifier on this data to predict movement versus resting state. So the microbit is just a really neat tool to run simple experiments on an edge device and really get a feel for the limitations of that device, um, to achieve some interesting results. So I highly encourage you to take a look at it. I really like it. I have one somewhere around here. Maybe after the break, if we have some time, I'll just show you the real unit. I have to find it. But here we'll be simulating the microbit in Python. So the microbit had its own simulator on their website. Let me try looking for microbit simulator. Yes, so the microbit has its own simulator where you can run code. You can program the microbit with, I think, three different languages. One language is this Scratch language where you can just use, these blocks and put the blocks on top of each other to create programs. Or you can write in JavaScript, or you can write in Python. So for example, if we switch to Python, here is our Python problem. We can go back to blocks, and here is our um, blocks problem. And then the simulator itself, let me see if we can. Well, it runs whatever problem was set up in blocks. Let me open one of their projects to show a more interactive version of this simulator. Okay, microbit simulator projects. I think we need. Yeah, so for example, this heart project. If we open this heart project in the simulator, I guess we need to open it in MakeCode. Yes, open it in MakeCode. So here, this program is very simple. In terms of blocks, it just shows the heart shape on start. So it just turns on and shows the heart shape. And you can see the simulator here. Um, whoops. And you can interact with it. You can press the buttons. So if your code supports buttons, you can press them. You can interact with the sensors, I think, with the LED. And then, well, you can restart it. And then I think if your simulation supports it, if your simulation supports acceleration properties, you can even rotate it here. It's not allowing me to, probably because it's turned off right now. But if your code includes some movement or movement tracking, then you can even rotate the microbit here to record that movement action. So this is a pretty neat simulator. Unfortunately, it's very hard to interact with. So we created our own version of the microbit simulator written in Python, and it incorporates the limitations, the memory and processing limitations of the real microbit. So we'll be able to experiment with data processing as if it was happening on the microbit. In that workshop on AI and machine learning that I mentioned, we connect the microbit to the computer, and then we pass data from the computer to the microbit, and the microbit performs computations in real time. Unfortunately, it's not really feasible in our current format. That's why we are using the microbit simulator. So the microbit simulator here, whoops, wrong button. The microbit simulator here has the maximum RAM requirements and the maximum storage requirements. Let's see, the microbit has 128 kilobytes of volatile RAM. So it does not support, processing of large data sets. It has only 128 kilobytes. You cannot load too much data onto it. Typically, when you interact with edge devices like this, it's nice to use them either for very simple processing that could happen on device or purely for data collection and data output. So you can record data from the microbit and immediately pass it to the computer, process it on the computer, and then send the result back to the microbit to display it. Again, because of the memory and processing power limitations. So here we have our microbit defined as a Python class, and we will be building this class and incorporating new functionality to the microbit as if we were working with the real thing. So currently, if we look at this microbit class, we can see that we have a function called output to screen written for us, and it takes this positions thing, this positions argument, which, as real microbit does, displays, or I guess it lights up the LED at specific positions. So you can tell the microbit to highlight LEDs at specific positions. So for example, here it highlights specific shapes. But if we look at the grid, it'll give us the row and the column of the LED that is currently being highlighted. So that function output to LED mimics that. If we give it the positions to highlight, it will highlight them in the output, and that will correspond to the microbit flashing those LEDs. And then it has a bunch of other functions that we will need to write with the help of AI. Okay, so I run this, yes, I run this cell to load the class into memory. So let us now look at the input design for our microbit or microbit simulator. Here we will model input from the temperature sensor embedded into each microbit. And we need to understand how the data is processed on device, how the sensor data is processed on device. So on the real device, the data arrives timestamp by timestamp as tiny voltage pulses over serial connections. And so we need to instantiate a continuous signal loop, assuming it was received and is being stored in a buffer. So the microbit has this small memory buffer of 128 kilobytes, maybe a little bit less than that, because you still have your codes running on it and current CPU caches. So, but it still has some memory, so it can accumulate some data that it reads from the sensors. It cannot accumulate too much; it'll overflow. So periodically, you will have to release that data and send it, say, to a computer. But it can accumulate some of it. So we will write a Python function, generate temperature signal, that takes the input sampling rate in hertz, the length of the signal in milliseconds, and a random seed for reproducibility, and will generate a 1D array with temperature readings. So each temperature reading will be sampled from a 20 to 30 degrees interval, and that's temperature in Celsius. And each temperature reading is a sum of the actual temperature and some device-specific noise, which should be distributed normally with some small standard deviation. And then, following the exactness principle, it specifies which libraries it needs to use. So let us write such a function. So this function will generate temperature readings for us that then the microbit can record with its sensor. Let me open a new ChatGPT window to enhance performance. Okay. Oops. Oh, didn't properly copy. That's, well, I pasted it in a different cell, but that's okay. So let us quickly review what's going on here. So it takes the random seed for reproducibility and fixes it. It generates the temperature randomly from the uniform distribution as we instructed it to, and it adds some device-specific noise. Now we generate a 5-second signal sampled at 100 hertz with fixing some random seed. Okay, so it throws an error. It's a type error, and it says generate temperature signal got an unexpected keyword argument called random seed. So we can prompt the AI to solve this, but we can immediately see the problem here. The names of the parameters that we give here to the function, they do not match the names that are specified in the function here. You see, because it's a sampling rate hertz, that matches, length milliseconds, that matches. But then here we call it random seed, and here it's called seed. So that's why we get this unexpected keyword argument random seed. Easy to fix, and just delete random and call it seed. And now our signal is generated. If we are unsure as to what the problem is, we can use the same strategy we used in the previous notebook. Just copy paste the function, this function, this row, and the error, and the AI will solve the problem for us. So here's our input, a random temperature signal sampled as, it says 100 hertz here, it samples at 1000 hertz. I think let's stay at 1000 hertz for clarity. But yes, if we are to sample it at 100 hertz, we need to replace it. We need to replace 1000 to 100. I think the proper option is 1000, proper, I mean, based on the analysis that follow, but I think it's a typo here in the instruction. So let me change it to 1000 here. So we have the generated signal. It's a random temperature trace, as if produced by the microbit sensor, microbit temperature sensor. Okay, so that part covers our data acquisition. So this is our data generated from the sensor. Now we proceed to the analysis module, and we are to um, program an on-device input processor. Let's look at the prompt. So for this prompt, we need to write the function read from temperature sensor, assuming input stream is a 1D array. The function should read the array element by element, check if RAM is available, and if so, save the value into the buffer. And it should print an error message if no more RAM is available and return 1. However, if it reads the full stream successfully, it should print the amount of RAM used and return 0. So to put it into context, this is the continuous input trace generated by the sensor, and hypothetically, it can proceed into the future. So it'll just go on and on continuously. However, as we discussed, we can only store as much on the microbit itself. And here we are assuming that we can store only so much data as we have RAM available. So we cannot exceed the available RAM. And here we will try to store the reading in the RAM as long as possible. And once we run out of RAM, we will quit and display an error message. Is the right prompt window? It is. Okay, nice. Great. Here's our function. And again, I'm emphasizing that we're specifically instructing it to make functions to ensure that we have the modular structure of our workflow. Okay, we can see that our error message is here and our success message is also here, so it's probably okay. Let us now try running it. Okay, it didn't display anything, which is concerning. That means something went wrong. So let us see. Oh, okay. So the problem is that I didn't read the instruction correctly. So we have to copy and paste the microbit class and modify the function directly in the class. Not we should not have it as a separate function because here we are calling our simulator, but the function inside the simulator is currently not defined. It's not implemented there. So let me fix this. Let me copy and paste the microbit class and then the prompt. So here's the microbit class. Here's our function read from temperature sensor. So I paste the class and then I paste the prompt. And let me just emphasize here so that it doesn't get confused. Write the function read from temperature sensor in the class above. Okay, so here is our function that we can copy paste inside the class. So it's called read from temperature sensor. Here's our microbit class, read from temperature sensor. As you can see, there's this to do implement using AI prompting. We paste it here. Then we can just run this cell again to reload this class into memory. Now we can run this cell. Let's see if it works. It does work. Okay, so the AI-defined function read from temperature sensor took our temperature signal, and it used 40,000 bytes, which is less than 128 kilobytes. So it was able to read the whole array successfully, and it returned 0 as we instructed it to. So here we were successful. All right, so we completed modules 1 and 2. We generated our temperature signal. This is our data acquisition part. We read our our temperature signal with the microbit and saved it in the buffer. This is our data processing part, or I guess the first step in our data processing part. The second step in our data processing part is to write an on-device output processor. So let's see. Here we have to write a function, again, inside this microbit class, process temperature data. It should read from the buffer value by value. And if the value is greater than 25, then the output to the screen should be located at position 2. Else it should output to screen at position 0. So it should flash the LED based on the value that is currently being read. It should either flash the central LED or the LED at position 2. So we already have our class, our microbit class, pasted to the prompt window. So we can just paste the prompt and we can specify that this function process temperature data should be inside the class above. Here's our function. Let us again copy paste it into the class. So here's our template, process temperature data. Here's the to do to implement it with AI. Just did it. So we can copy paste it and format everything nicely. So now the function should be ready. As you can see, the function itself uses that output to screen function we talked about previously. And so you just give it the coordinates to flash, and then it'll flash at those coordinates. Let me rerun that cell to reload the class into memory. And let us run the module and see if the processor works. It, in fact, does not work. And this is because we did not reinitialize the class. This is our oversight. This line, microbit equals microbit, should be present every time we change our class because it reinitializes the microbit definition. So whenever we change it, we need to reload it into memory. Still doesn't work. Okay. And it doesn't output anything. So let us see if we read. Oh, yes, right. Because, sorry, we have to redo both the reading and the processing because when we reinitialize the microbit, the temperature buffer gets nullified, so it's empty right now. So let's just reread the signal. Again, it fully fits in the memory. And then when we run the process temperature data, still doesn't work. Interesting. Okay, so let us ask AI then. So let us prompt it and try to solve this issue. Let us say I'm trying to run the following lines. So we are initializing the microbit. We are, oh, okay. I found the problem, but let's see if the AI finds it. We're running these two lines first, and then we're running these two lines second. And let us see if the AI can figure out what's wrong with this. But the second function does not output anything. What's the reason for that? It did. So as you can see, it says that we are creating a new microbit object before calling process temperature data here. So we first create the microbit, we read the temperature sensor, then we recreate the microbit. The temperature sensor data buffer is now empty, and they process the temperature data. So the proper way to do it is suggested here. We first create the microbit, then we read from the temperature sensor, and then we process temperature data. So let us incorporate this suggestion. To incorporate, we have just remove that line. So again, these are these three lines that it suggested. Initialize the microbit, read from the temperature sensor, and process temperature data. Perfect, it works. So as you can see, it emulates the microbit LED screen, and the LEDs that are not active are shown as these squares, and the active electrodes are shown as these stars. And well, it's pretty jittery because it outputs every temperature value, and the temperature is sampled at 1000 hertz. So given the natural delay here for visualization and processing, it's still pretty fast. So that's why it appears as it's continuously changing. And our data is randomly simulated, so it's expected that that there are both values greater than 25 and below 25 sampled approximately uniformly. So it's expected that the visualization jumps between the 2 points that we instructed it to. Okay, so this is our on-device processor plus visualizer, modules 2 and 3. And finally, the resource usage logger. Now we have to change our microbit class, and we have to write the function to file, which takes the file name and appends the current time. And then we specify the Python function to do that to ensure exactness, and the current RAM used. If the file does not exist, the function should automatically create it. So we modify the class, and then we have to test it with our function below. Okay, so it should again create a file, save the current date and the current RAM used. Let us do that. Let us emphasize that it's inside the class. Okay, so it creates some file and writes time and RAM. So this looks good. And now here's our function to file again with the to do. Let us replace it. And now we have our fully functional microbit class. Now the challenge is to properly run everything. So we initialize the class. The signal, we don't have to regenerate the signal, but we have to reload the class into memory, read from the temperature sensor. Now we have to process temperature data. Let's wait for it to process. Okay, and then let's try saving to file. Okay, um, the code ran successfully, so it looks like it saved the file. Let us check. Here is our out.txt. And indeed, it saved the current date and the amount of RAM used. And we can validate it with the cell above, that the used RAM is indeed 40,000 bytes. All right, so that concludes this notebook. There is an interactive playground here to experiment with the microbit. So here you're encouraged to generate input that will make the microbit run out of RAM, given the RAM limitation above, and then include some modifications to the read from the temperature sensor functions and function and the process temperature data function. So I highly encourage you to experiment with that, play around with visualizations, and should you have any questions, feel free to ask them in the chat. Okay, question from EV out.txt. 3 instances of microbit. Not fully sure. So let me scroll down to here. So this is the full single pass of the pipeline consolidated into one cell. So to file. So what will happen here is it will initialize the microbit, initialize the temperature signal, load the temperature signal into the microbit, process the temperature data, and then save the amount of RAM to file. So it will add one line to that file. If we load some additional data into the microbit and resave it, then depending on how we define that function above, it will either append to that file or fully rewrite it. So we'll need to check depending on what we want, and then if that behavior is not what we want, we can go back to AI and say, I want to always append to that file, or I want to always overwrite that file. Okay, great. All right, so this concludes notebooks 2 and 3. I will stay here